Hi there, Rachel Sherman here, and in this video we're going to explore set cardinality and also proving countably infinite and understanding what the terminology means. Set cardinality is always referring to the size of a set, whether it's the unique number of elements in a finite set or the unique number of elements in an infinite set. And what we'll be seeing over the next few slides is the difference between countably infinite sets and uncountably infinite sets. A few things that you may find helpful with cardinality. The first is going to be that cardinality is denoted using an n. So if we're talking about set A, for example, we would say the cardinality of set A is n of A. So it looks very similar to function notation. Just remember that if these were finite sets, you would be counting the number of unique elements that exist. A few other things you may find helpful about cardinality is the following. Cardinality is reflexive. The size of a set is, of course, the size of itself. It has to be the same if you're counting the same set in cardinality. The cardinality is also symmetric. If you have two sets A and B and their cardinalities are the same, it's the same thing in reverse. And also, something we've seen before in our discrete math course is that transitive property still holds true. If the cardinality of sets A and B are equal, as well as the cardinality of sets B and C, then we know by the transitive property that the cardinality of A is that also of the cardinality of set C. So let's look at what it means to have countably infinite sets. You can prove that sets have the same cardinality by pairing off their elements. Specifically, you can make these proofs by showing that a bijective map exists from set A to set B, whether these are finite or, of course, countably infinite. A set is countably infinite if and only if we can match its elements to that of the natural numbers, which are also known as the positive integers. So for proving purposes, you can use either of these sets. We can also prove that these two sets are in fact the same by the techniques that we're going to show throughout the rest of this video. Prove that the set of integers are countably infinite. So if we want to show that the integers are countably infinite, you have to pick one of these sets to match it to. For simplicity's sake, I'm going to go with the natural numbers. Remember that your natural numbers begin at 1 and go off to positive infinity. So you want to start by taking a moment to write these out. There's not necessarily any requirement as to how many, but as with things that you've probably seen before, you should always generate a list long enough to show that the pattern exists. Now, writing out the set of the integers can be a little bit more tricky, but remember, you're talking about positive and negative whole numbers, including 0. The only thing that doesn't have a partner here is 0. So I'm going to start my list with 0, and then alternate positive 1, negative 1, positive 2, negative 2, so on and so forth. And we've generated the pattern to show that the additive inverses are accounted for. So although it's bouncing back and forth, we started with 0, we've got then all of our values thereafter with enough of a pattern to follow through. Now, once you have that list, what does it mean to have a bijective map? You're mapping from your domain, which in this case is going to be the integers, to our codomain of natural numbers. For it to be bijective, each input can only go to one output, and every value in your codomain must be used eventually. So I'm going to start and just map them in this order. 0 will map to 1, 1 to 2, negative 1 to 3, 2 to 4, negative 2 to 5, and then if you kept this list going, you would map 3 to 6, negative 3 to 7, so on and so forth. So if this pattern continues, you've shown that there is now, in fact, a bijective map from the integers to natural numbers, therefore their cardinalities have been proven to be the same. And for the most part, you can do this with a bunch of different things, although it may not always seem intuitive. Prove that the integers have the same cardinality as the even integers. So we've already played around with the integers, so let's jot this list down again. So we have 0, 1, negative 1, 2, negative 2, and so on and so forth. The even integers we can denote as 2z. 0 is still even, specifically an even integer, but then you would have positive 2, negative 2, positive 4, negative 4, and so on and so forth. And then just like we did before, go ahead and map. 0 will map to 0, 1 to 2, negative 1 to negative 2, so on and so forth. Now, technically speaking, this isn't the only way that you could go about this. You could choose to use an ellipsis on either end. You just have to be a little bit more cautious if you've got positive and negatives and you're using the ellipsis on both ends, because that would require you to map things and cross over. It can get a little bit tricky to look at. So I would always recommend, if you can figure out the pattern to show how a pattern could work to describe this in a one-ended ellipsis, you're always going to be better off and find a much easier way of mapping your values. Now, instead of using this video to also describe how the positive rational numbers are countably infinite, I've included a separate link in your D2L page to show you what's called the diagonalization style of proof. Essentially, it uses pattern base to help you avoid having any repetition in your list, subsequently giving you a pattern-based list for something that could be very confusing to do, like the rational numbers. Now, something to keep in mind is while the rational numbers are countably infinite, and again we use something called the diagonalization proof, you have to remember that being that this is a discrete math course, not every set that we deal with is going to be countably infinite. Now, think for a moment about everything we learn about throughout the semester, whether it's from set indexing, which we always deal with either natural numbers or positive integers, or what ended up happening when we ran into that real number system. So on day one of a discrete math course, you would have the conversation of what are cases where things are countable versus uncountable versus discrete, continuous. So there's a lot of vocabulary that goes into this. The real numbers are not countable at all, and the concept behind it is as follows. Give me a list of numbers that you feel is comprehensive on the real number system. Any list at all. And something that you may find a little bit thoughtful here is that there are uncountably infinite numbers, of course, in the real number system, but also if you look at a subset of that. So if x is a real number such that it's bound from, let's say, I don't know, -5 to +5. So just between -5 and +5 on the real number system, you have uncountably infinitely many numbers. You could pick any values here, right? You could even say from -0.5 to +0.5 or -1 to +1. You could even say just from 0 to 1. Any of those would still yield uncountably infinite results. And the reason I would say that, and the way that you would show why the real numbers are not countable, is there's no way to come up with a pattern. So if you gave me a list, or if anyone handed you a list of a pattern, so let's say we have this value here. I'm just going to come up with some numbers off camera for a moment. All right, so now that we've got this list, although it's a small list, the concept is generally the same. So if you handed me this list and said, okay, well, hey, Rachel, here's a comprehensive list of all the real numbers. I've got a pattern going. Here it is. Here's the pattern base. I promise you that just based on this list, I can find at least one value that's not on it. So excusing the obvious for a second, start by looking at your tens place. So we've got a 0 here. Let's find something not on the list. Oh, there's a tens place with no 3. So here we go, 0.3, not on the list. And you say, oh, okay, well, I just forgot that one. Okay, well, I'd say, okay. So I keep going down this list. Oh, what about 0.6? And hypothetically, even if you came up with a million values where they all had a 1 here or a 2 or whatever, just go to the next decimal place. So let's say that you had all of the zeros listed. Okay, well, what about 0.03? Is that on the list? Nope. How about 0.04? Also not on the list. So the concept of why are the real numbers uncountably infinite? There is no way to generate a pattern for them. If you are unable to generate a pattern for a set of numbers, then there is of course no way for you to match them up in a bijective manner with the natural numbers, which are countably infinite. Thanks for watching this video.